Hey, welcome back everybody. In this lesson we're going to talk about torque and horsepower, what makes them alike and what makes them different. Those are two important mechanical concepts for your program, and we're going to try and get a little bit better understanding of those and how math ties those two together. So by the end of this lesson you'll be able to calculate torque and calculate horsepower. And know what makes those two things different. Let's start by talking a little bit about torque. So a torque is formed when you apply a twisting force on an object. And in fact, a lot of people will say that torque is nothing more than a twisting force. But how much twisting force you generate depends on two things. It depends on how long the lever is that you're using to apply the twisting force, because you have to have some sort of a grip or a lever on something anytime you twist it, and how much force you apply. So if we want to calculate torque, what we do is we multiply the force that we're applying times the length of the lever arm. And so all those things have to have units on them. The force that we apply typically we'll use pounds. If we were using metric units, as you know, the metric unit of force is in newtons. And for the length of our lever arm, usually that's in inches or feet, but for our purposes, we are always going to put the length of our lever arm in feet. Because if you multiply a force in pounds by a lever arm length in feet, you get the units of torque, which are foot-pounds, or some people say pound-feet, same thing. So these three units, foot-pounds, pounds, and feet for our lever arm, will be the units that we use for all three of these in all the work that we do. Now the relationship that torque is equal to force times lever arm is represented by what I like to call the TFL circle, or the torque force lever circle up here. And the TFL circle looks like this. If you want to find torque, you can just cover up the T, and since F and L are right next to each other, that means that those two things get multiplied together. T is found by multiplying F times L. But you can use this circle in two other ways as well. One other way is to say that if we're trying to find the force that we need to apply, we can cover up the F, and since T is over L, that means we would divide the torque that we're trying to create by the lever arm length that we have to twist with. So force can be found by taking T divided by L, or our torque divided by our lever arm. Or if we're trying to find the length of the lever arm that we need in order to create our torque, we can divide the amount of torque we want to create by the force that we have available to apply. And if we know those two things, we can divide them, and that will give us the length of our lever arm. I would recommend copying down this TFL circle on your formula sheet. This will be one of two formulas that we're going to use a lot in our work today. Okay, so let's start with this question. When you tighten down a lug nut with a torque wrench, you're creating torque. And so my question is, if you apply 120 pounds, that's a good part of your body weight, to the end of a 16-inch torque wrench, then how much torque are you creating? That is to say, how many foot-pounds of torque? Well, let's work that out. So for starters, let's refer to our TFL circle up here. The question is, how much torque? And so if we're trying to determine a torque value, then we can note that the amount of torque that we're going to create is found by multiplying the force that we're applying by the length of the lever arm. Now, we know how much force that we're applying. That's going to be 120 pounds. Our 16-inch torque wrench, though, that's our lever length. We need that to be in feet. And so we have to do a unit conversion here. So let's take 16 inches. Put it over 1 as we've done before. We know that there are 12 inches in 1 foot. That'll make our inches cancel off. And if on your calculator you take 16 times 1 divided by 12, though you know you don't need to multiply by that 1, you'll get 1.333 feet. And we'll leave 3 decimals on there to avoid rounding error. So that's 1.333 feet. And that is our lever length. So now let's find our torque. T is equal to F times L, and so a force of 120 pounds times a lever length of 1.333 feet. or that reduces to 4/3. And if we multiply that out, we get about 159.9 something, close enough to round off and call 160 foot-pounds. And that's the amount of torque that we're creating, 160 foot-pounds or 160 pound-feet of torque. And that answers the question. Now, if you wanted to create more torque than that, because the lug nut wouldn't break free if we were trying to loosen it, you have two choices, right? How do you create more torque? Well, either you need to apply a greater force, you need to push harder on your lever, or you need a longer lever. That is to say, you need to cheat a little bit and get a cheater bar. Okay, well, you start learning about torque at a pretty young age if you sit on a seesaw. So I want to look at an example with you here. There's two kids sitting on a seesaw, and you know that that they can balance each other if they adjust where they sit. So on the right side is a smaller child, 50-pound kid sitting 6 feet back. Well, we have the amount of force he's applying due to his weight, and we know the length of the lever he's using. He's sitting 6 feet back. So his torque is going to be his force times his lever length. That is to say 50 pounds times 6 feet. And if we do that, we end up with 300 foot-pounds of torque. Nice job, kiddo. 300 foot-pounds of torque. That's a lot of torque. Now, his torque is, in this picture, clockwise. Now, his big brother, he's creating torque in the opposite direction. He weighs 80 pounds. That might be a little bit hard to see in your picture, and he's sitting 3 3/4 feet back. So his brother's torque is his force, 80 pounds, times his brother's distance, 3.75 feet. And if you multiply those together, you also get 300 foot-pounds. So they're creating the same amount of torque, and therefore they could go back and forth all day long. So I want to follow that up with one more question. Suppose the little brother has a little cat that comes and sits on his lap while he's sitting on the seesaw, and the cat adds 10 pounds. So he's no longer 50 pounds, he's now 60 pounds. But he doesn't scoot in or out. It's just that his force goes from 50 to 60 because now he's got a cat sitting on his lap and he weighs a little bit more. 60 pounds times 6 feet means that his torque will go up. He will now be creating 360 foot-pounds of torque on his side. Now what's the brother going to have to do? If his brother stays right where he is, he's still only going to make 300 foot-pounds of torque. He'll go up in the air and sit there because his brother is creating more clockwise torque. So what's he going to have to do? He's going to have to scoot back a little bit. And so the question is, how far back should he sit? What size lever length should he create if he wants to match that 360 foot-pounds? Well, let's answer it down here. To find the length of the lever he would need, we're going to take T over F, that is to say the torque, and divide it by the force. Now we know how much torque he wants to make. If he wants to balance his brother, he needs 360 foot-pounds. But he still only has his weight to apply, and so that's going to be 80 pounds. Now notice, just like when we were doing unit conversions, the pounds is on the top and the bottom, it cancels off. And we end up with 360 divided by 80, which turns out to be 4.5 feet. So he's going to have to scoot back a little bit and not sit 3 3/4 feet back. He's going to have to sit 4.5 feet back. And if he does that, then they can continue to seesaw, and his extra torque will balance the torque created by the cat sitting on the right side. Now your skill check for this topic will have a very, very similar question to that. So if that problem didn't make sense, rewind that and watch that one more time and follow along those changes of numbers, and let me know if you're still stuck. But that's an important concept for you to understand. Okay, let's do one more. The question is, how much force do we need to apply to a torque wrench if we want to torque the head bolts on an engine down to 90 foot-pounds? We have a 15-inch torque wrench to use. The question is, how much force? So we're trying to find F on our torque wheel. So we are told by the wheel that force is found by taking our torque and dividing it by our lever length. Now we know how much torque we want to create. We want to make 90 foot-pounds. And we're going to divide by our lever length, which would be 15 inches. But this always needs to be in feet, so we need to do another unit conversion. Let's do that up here. 15 inches. And we're going to multiply by 1 foot over 12 inches. That makes our units cancel off. And 15 divided by 12 is 1.25, or 1 1/4 feet. So 90 foot-pounds divided by 1.25 feet turns out to be 72 pounds. The feet canceled, and so that leaves just pounds, which should make sense because we're trying to find a force after all. And so you're going to have to apply 72 pounds. If you can't muster up 72 pounds to apply to that torque wrench to torque those head bolts, well, then you better get a longer torque wrench to help you generate that 90 foot-pounds of torque. Okay, when a winch winds up cable on its spool, it's using concepts of torque in order to do any pulling. So if you were to picture what this looks like, if we wind up all of our cable around the spool on there and hang some weight on it, I think you'd agree that that motor has to create some amount of torque in order to wind up the cable. So if we're going to try and lift 2,300 pounds, which is the capacity of this winch, and the motor is capable of twisting with 400 foot-pounds of torque, then the question is, how long is the lever? Now you might look at this picture and say, well, there is no lever in here, but there is. The lever is the distance from the point where it twists, or the center of our spool, out to where the cable winds up. Now for a winch like this, that'd always be changing, because as the cable winds, the radius gets bigger. But our lever length is just the radius of the circle. And remember, radius is from the center to the edge. That's kind of how a steering wheel is too. You grab the steering wheel to create a twisting force on the steering wheel. The radius of the steering wheel is the lever that you're using, which is why older cars had big steering wheels, because they didn't have power steering yet and they needed you to create more torque. If we want to find lever length, we better divide T over F. So L is equal to T over F. Now we know how much torque we have. We have 400 foot-pounds from our motor and gears. We know how much force we're pushing against. That's 2,300 pounds. Pounds cancels. And then we're left with 400 divided by 2,300. If you do that on your calculator, you get about 0.174, and the only units that didn't cancel there are feet. 0.174 feet. Now that's a little bit hard to think about. Let's turn that into inches, even though the problem didn't ask us to do that. 0.174 feet. We'll multiply that by 12 inches over 1 foot to make the feet cancel. And that turns out to be about 2.09 inches. Now keep in mind, that was the length of our lever, that is the radius. The question is, what diameter of spool would we have? Diameter is the distance all the way across. So from the outer edge all the way across to the outer edge, that's going to be 2 radius values, or 2.09 times 2, and that gives us a diameter of 4.18 inches. And that seems about right. It's going to take about a 4-inch spool in order to make that winch work effectively. Okay, well let's move on and work with horsepower for a little bit. The thing that you might notice about torque is that there's no place for the time to be taken into account, because torque, it doesn't matter how fast you turn. All that matters is that you provide that force over some lever length. Horsepower takes into account both the torque that you're creating and the speed at which that torque is created, which is usually your engine speed. So that means that horsepower can be found by taking torque times the RPMs of the engine, which is what we'll be talking about, and divide it by 5252. Now you're probably going to wonder, where does that number 5252 come from? The math behind that is a little complicated. It takes into account the definition of what a horsepower is and the fact that we're turning in circles. And if you're interested in a little bit more background on where that number comes from, shoot me a text or an email and we'll get online and chat about it, and I can show you how that number is derived, but we're just going to kind of accept it for what it is right now. So the math here is pretty easy. You're going to want to write this formula down on your conversion sheet. This is one that we'll use a lot, but it's easy to use in practice. How many horsepower are produced if an engine makes 185 foot-pounds? So that's telling us how hard the engine twists at 4,200 RPM. That's telling us how fast the engine is twisting. Let's work that out. Okay, we can just plug and chug directly here. Our horsepower is found by taking our torque, which is 185 foot-pounds, times our RPM, which is 4,200, and we're going to divide that by 5252, and that just becomes a basic calculator problem. We'll round that off at the nearest tenth, and you should get 147.9 horsepower. Go ahead and type that into your calculator and verify that you're getting the same result. And that's all there is to it. So I've got a picture of an engine dynamometer here, and you've seen or are familiar with engine dynos or chassis dynos for that matter. Dynamometer always measures torque, and then it calculates horsepower at those different speeds, and we're going to do that in just a minute. Before we do, I'd like you to take a minute and do this problem. When you're sitting at a stoplight at an intersection idling, your RPMs are very low. So my question is, if your engine is making 85 foot-pounds of torque, but only at 800 RPM or idle speed, how many horsepower is that? Take a minute, pause the video, reach for your calculator, and do that calculation, and then unpause to see if your solution is correct. Okay, well our torque is 85 foot-pounds and our RPMs are just 800. We'll plug those directly into our horsepower formula and we multiply those and divide by 5252 and you end up with about 12.9 horsepower. So that's not very much, and that should make sense because when you're sitting at a stoplight, the engine doesn't need to make much horsepower. It's just turning your alternator, your power steering pump, if it has one, your coolant pump, and a few other accessories, and that's all it's doing. When you want to take off from that stoplight, you hit the accelerator and your engine will create more torque and at a higher RPM, and all of a sudden your horsepower will jump up and you're rolling. Okay, here's our last problem from this section, and this is going to give you a little bit of an insight into the way torque and horsepower are related. So here's what we're going to do. This is a plot of engine torque over the power band of an engine from 2,500 up to 6,500 RPM. This was measured on a dynamometer. This is only the torque value though. These are not the horsepower values. So you can see this engine makes the most torque around 4,500 to 5,000 RPM. That's kind of typical for a gasoline engine. A diesel engine will make its torque down around 2,000 to 2,500 RPM, much lower because the fuel burns more slowly. So here's what we want to do. We want to also put a horsepower curve on here, and I want you to see an interesting characteristic. So for starters, if we want to turn these into horsepower values, we have to read what these torque values are. So for starters, look at 2,500. At 2,500 RPM, it looks like the torque value is between 250 and 300. You might decide that that's about 260 foot-pounds of torque right there. Okay, 260 foot-pounds of torque. Now let's look at 3,000 RPM. At 3,000 RPM, it's just a little bit over 300 foot-pounds of torque, probably about 305. 3,500 RPM, it's a little bit higher than that. There we're up to 310. 4,000 is getting closer to 350. It looks like that's around 330. 4,500 is just under 350 foot-pounds of torque, about 348. And then at 5,000 RPMs, it starts to drop a little bit. At 5,000 RPMs, it looks like we have about 345 foot-pounds. Now, those aren't exact values, but pretty close based on how we're reading the chart. Now, we can turn these torque values into horsepower values, right? We can take the RPM times the torque to get a horsepower value. So for our first one, for example, 260 foot-pounds of torque times 2500 RPM divided by 5252, that means that we are producing 124 horsepower at that engine speed. And we can plot that, and we will in just a minute. You can repeat that for all these values, and as you can see, our horsepower goes up. And now we can plot those. So I'm doing those all at once here, but at 2500 RPMs, we have about 124 horsepower. So that gives us our red curve, which is the horsepower curve. It climbs to 174, and that climbs to 207, up to 250, 251 actually, 298, and we're up to 328. And so you can see the horsepower is climbing as we rev that engine higher and higher. Okay, I want you to pause the video, and I want you to read the torque values for 5500, 6000, and 6500 RPM to complete that table. Write those down. Reach for your calculator and use the horsepower formula to calculate those 3 horsepower values. Go ahead and do that. Unpause the video when you're done. Okay, your numbers might not match mine exactly, but they should be pretty close. At 5500, we're at around 335 foot-pounds of torque. At 6000, you're right between 300 and 350, or at about 325 foot-pounds of torque. And at 6500, we've dropped off again down to about 305 or maybe 310. Those should be the numbers that you read off the chart, approximately. And then when you plug those into the horsepower formula, multiply the torque by RPM and divide by 5252, you should get 351, 371, and 377 or so. You could be a little bit off from that. And then if we plot those, it finishes off our horsepower curve. So our red curve is now our horsepower curve. That completes the table. Now, they're not the same curve. You'll notice the peak torque curves between 4500 and 5000 RPM. That's when the engine is twisting the hardest. But it's actually doing more work more quickly up at around 6500 RPM, and it looks like it's about to flatten up. But that's also really common for a gasoline engine. But here's the thing I want to draw your attention to. Right here, these two curves cross. Torque is on its way down, horsepower is still on its way up. What RPM is that? It looks like it's somewhere between 5000 and 5500 RPM, right about there at that green line. Well, what engine speed is that? Well, it's 5252. The torque and horsepower curves always cross at 5200 and 52 RPM. That's for every single engine on the planet. Why is that? Well, yeah, you recognize the number 5252. It's directly from our horsepower formula. If you take the torque and multiply by the RPM and divide it by 5252, you get the horsepower. That means that when your RPMs are at 5252, when an engine is turning 5,252 RPMs, you plug that number in and it cancels top and bottom. And that means whatever your torque is has to match your horsepower value. So these two curves always cross for every engine, whether it's a lawnmower or a Peterbilt truck or a Lamborghini. They always cross at that point. Torque is on its way down, horsepower is on its way up at that point. Okay, you're going to do some more of these types of graphs in your practice problems for today. Make sure to watch that example again if that's not clear. Okay, so that wraps up this lesson. The two main things that you can now do, you can use the TFL circle, the relationship between torque, force, and lever arm, to calculate either the torque, the force, or the lever arm, given the other two. And if you're given the torque and RPM of an engine, you can use that to calculate horsepower and even make a horsepower versus torque curve. All right, that's it. Go ahead and let me know if you're stuck. Otherwise, we'll see you in the next lesson.